Suppose we have a small set with just 6 elements in it, and we pull 2 in a row. List all the outcomes. This is really 4 questions. Because the 2 questions that are very often asked in combinatorics are, do we have replacement, and does order matter? So, okay, let's start with replacement, order matters. You actually have seen this question already. Replacement means that we pull the first number and then throw it back. So it is possible to pull the same number twice. That's often not the case, right? When we are pulling the lottery numbers, we don't throw back the first number before we pull the second one. This one is the same question as how many 2-digit numbers can be formed out of these digits, right? In a 2-digit number, 34 and 43 are different numbers, so order does matter, and 22 is a reasonable 2-digit number, so replacement is allowed. So the sample space would be, I'm going to put a comma there, but feel free to just think about the 2-digit numbers. So it could be a 1, 1, a 1, 2, a 1, 3, a 1, 4, 1, 5, 1, 6. Did you figure out how many outcomes are possible? Because order matters. 1 and 2 and 2 and 1 are different cases. So we're going to have, this is the same thing when rolling a die twice, right? Why do we have replacement? Because the die never remembers. So 3, 1, 3, 2, 3, 3, 3, 4, 3, 5. Okay. So now let's say, so here we have 36 cases, and we have already seen examples for that. If you roll a die twice, this is the list of possible outcomes. So in case of a die roll twice, the order does matter and replacement is allowed. What if order matters but no replacement is allowed? So no replacement is allowed means that we cannot pull the same number twice. So 1, 1 is not allowed, because once we pulled 1, we don't replace it, we don't throw it back. So then, no replacement, order matters. And this would be, okay, so we have 1, 1 is not good, 1, 2 is good, 1, 3 is good, 1, 4, 1, 5, 1, 6. Then we move on, the first row being, the first number pulled being a 2. So we have 2, 1, 2, 2. 2, 2 is not allowed, so we're going to get 2, 3, 2, 4, 2, 5, 2, 6. Did you figure out? Jesus. Did you figure out how many outcomes are going to be? So 3, 1 is okay, 3, 2 is okay, 3, 3 is not, so we skip that, 3, 4, 3, 5, and 3, 6. Then 4, 1, 4, 2, 4, 3. 4, 4 is not allowed, we skip that. 4, 5, 4, 6. In the column with 5 first, we only skip 5, 5. The rest is cool. And the one where the first number pulled is a 6, only 6, 6 is not allowed. So we have 30 outcomes. Can we think of it combinatorially? We can say, okay, the first number we pull can be 6 different, but then the second one can be only 5 different, and that is your 6 times 5. This would be equivalent to asking how many 2-digit numbers can be formed out of these digits if repetition of digits is not allowed, right? Okay, we're going to see this a lot. How about no replacement and order doesn't matter? So when we look at this original sample space, when replacement was cool, order mattered, we had the first can be 6, the second can be 6, so we had this nice 36 cases. How would this list be adjusted if replacement is not allowed? That rules out the diagonal, right? These have to be kicked out, so we're down to 30. But what does it mean order doesn't matter? Order doesn't matter means that the case 1, 3 and 3, 1 need to be identified. This should be counted as one case. And what kind of a question would that be? Remember, for example, when we list elements of a set, the order in which they are listed does not make the set different. So we could ask, how many 2-element subsets of U? And then notice that I'm going to use the arrangement for our benefit. So basically what's going to happen? From the first column we kick out 1, 1 and the rest is cool. So we're going to have 1, 2, 1, 3, 1, 4, 1, 5, and 1, 6. Now from the second column, 2, 2 has to go, and 2, 1 has to go because we already counted as 1, 2. But then the rest, 2, 3, 2, 4, 2, 5, 2, 6, those are new cases. So we're going to get 2, 3, and notice that I'm going to write next to the 1, 3, 2, 4, 2, 5, 2, 6. Now what about the column with 3? Well, 3, 1 is already counted as 1, 3. 3, 2 is already counted as 2, 3, and 3, 3 is not allowed, so we start with 3, 4. So it's getting smaller and smaller, When we move on to 4, 4, 3, 4, 1, 4, 2, 4, 3 are already counted as 1, 4, 2, 4, 3, 4, and 4, 4 is not allowed, so we start with 4, 5, 4, 6, 4, 6. And then with 5, well, 5, 1 is already counted, 5, 2, 5, 3, 5, 4, 5, 5 is not allowed, so 5, 6, and that's it. So basically from this, we just get thing below the diagonal. The diagonal is out because replacement is not allowed, and then everything above the diagonal can be identified with something below the diagonal. So instead of a rectangular region, now we get a nice triangular region. And so we have 5 plus 4 plus 3 plus 2 plus 1. 1 plus 2 is 3 plus 3 is 6. 6 plus 4 is 10, so we have 15 cases. Which makes sense. If we remove the 6 from the diagonal, we get 30, and then it's exactly half of that, right? So we have 15. To be honest, these are the 3 that I frequently see in combinatorics. The 4th one is a little bit stranger. The 4th one is, and usually that's the most difficult, I think. So the 4th one is replacement is allowed and the order doesn't matter. Can you predict what we're going to get? Let's look at our original outcomes. Replacement is allowed, which means 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6 are in play. They're fair game. But order doesn't matter means that 1, 2, and 2, 1 need to be identified. This time a bigger one because the diagonal is included. So we're going to get 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. And then we roll up to 2. 2, 1, well, order doesn't matter, so 2, 1 should be identified with 1, 2. 2, 2 is cool, and then all the rest is fair game. But because order doesn't matter, we're going to get this nice triangular shape. Because stuff above the diagonal, all of them will be listed already below the diagonal. The only difference from the previous case, can we figure out how much we're going to get? So basically, we're going to get this and throw in the diagonal. So we're going to add 6 to this. I predict 21 outcomes here. So 3, 1, 3, 2, 3, 1 already listed, 3, 2 already listed. So we start with 3, 3, and then 3, 4, 3, 5, 3, 6. And then we roll up to 4. 4, 1, 4, 2, 4, 3 are all listed. 4, 4 is allowed. And then 4, 5, and 4, 6. We roll up to 5, 5, 5, 5, 6. And finally 6, 6. So we have 1 plus 2 plus 3, which is 6, plus 4, which is 10, plus 5, which is 15, and we add 6 to that, so indeed we have 21 outcomes. So these are the possible outcomes in the four fundamental cases in combinatorics with regards to whether replacement is allowed or not and order matters or not. This one we throw a die twice, right? The next one is, or how many 2-digit numbers? This one would be how many 2-digit numbers with different digits. The next example was how many 2-element subsets are there for the set U, and the answer is 15. And finally, what does could be? What kind of a question? Well, we can come up with a question like how many 2-digit number where the second number is no less than the first number, right? Because that's these guys here. Try to think about a more natural example. Okay, thank you for watching.